we discuss all the aspects, how to enter data in SPSS, how to label different kind of variables, how to categorize variable, and how to make transformations, and how to import and export files. So all these things we discussed last time. And moreover, I also discussed about different kind of scales, if you remember: nominal scale, ordinal scale, interval scale, ratio scale, and also some part of the descriptive statistics, so that interpretation becomes easy, like skewness, kurtosis, mean, median, mode, percentile, deciles, right? So all these things we have already covered. Now let's move on to a very, very important topic in statistics. They are known as testing of hypotheses. And in fact, this branch of statistics is called estimation and testing of hypotheses, which is basically a backbone of statistics, because entire inference, whether you should accept the hypothesis or reject the hypothesis, depends upon the knowledge of these tests. So today, because it has been mentioned that there is a discriminant analysis, then parametric test, t-test, and chi-square and f-test. So I will start with the parametric test, and in the second part we will do the discriminant analysis. The reason is because I will be talking about hypotheses, and in discriminant analysis, if I start with, then you may face difficulty. What is this hypothesis? So you should be clear about the hypothesis. So anyhow, there is a little bit of reshuffle. I'll start with the estimation and testing first, and then later on I'll cover up the discriminant analysis part. Okay, with this background, let's move on to the first part of the presentation, that is called parametric test or estimation and testing. So before coming to the parametric test, I'll just discuss few important points which are generally not elaborated in many books, like what is p-value, what is type 1 and type 2 error, what do you mean by the actual meaning of level of significance, critical region, and also different type of hypotheses, null hypothesis, alternative hypothesis, where to use one-sided, where to use two-sided, right? All these things I will try to clear right in the beginning, so that you should not face any difficulty, particularly in framing the hypothesis. So let me share the screen. Just give me one moment. I'm just sharing the screen, and then we'll move on. Hopefully you can see my desktop. Anybody?
Yes, sir. Yes, sir.
Yeah, thank you. Thank you.
Yes.
Yeah. So let me start with the presentation. So I will today discuss about the parametric test, chi-square test, f-test, t-test, because they are t-test and f-test, they are covered under parametric test. Chi-square is a non-parametric test, and in the later part I'll cover the discriminant analysis. Okay. Now, as I mentioned, estimation and testing of hypotheses. I mean, in order to test any hypothesis of the parametric test or the non-parametric test, we need to frame our hypothesis. So there are three words here. Please try to understand. One is estimation, another is testing, and the third one is hypothesis. And these t-test and f-test, they are covered under parametric test. Why they are called parametric test, I will focus today. Now, what is the difference between parametric and non-parametric test? I will also let you know. All right. So there are three words, as I mentioned: estimation, testing, and hypothesis. So we'll elaborate all the three words. So first of all, what do you mean by statistical estimation? See, there is always some kind of population. It is difficult to study the entire population. Everybody knows, because population is generally very large. Then what we do? We take a sample out of this population. And the sample we generally take is a random sample. Sample we take is a random sample. Now, what is the meaning of this word random? Random stands for that there is no favoritism, there is no biasness. What is the meaning of favoritism and biasness? For example, there are, let's say, 50 students in the class, and somebody give me this task that you have to select only 5. Now, it may be possible that I know the name of 5-6 students, and if I go by the name selection, then obviously there may be favoritism, there may be biasness involved. So what is the best way? Best way is to that I can write the name of each and every one of the 50 students on a piece of paper. There will be 50 slips, mix them thoroughly, and then pick up one slip at random. Now, this is just a kind of lottery system, right? I just pick up one slip at random, and whosoever name appears, that person gets selected, right? And this type of selection procedure is basically called a random sample. Random sample means every member of the population has the same chance of being selected into the sample. Every member of the population. There is no favoritism, there is no biasness. Now, our selection of the sample from the population depends upon various sampling techniques, which I will discuss in the next slide. For example, if I take out one slip out of 50, then what is the probability of selecting one person out of 50? Everybody knows it is 1 by 50. Now, suppose I replace this slip back into the container, and now there are again 50, mix them thoroughly, and then again pick up one slip. Either the same slip will appear, or it may be something else, right? But probability will remain 1 by 50. Similarly, if you replace back before the next selection, and again next selections are made out of the complete list, then this type of sampling is called simple random sampling with replacement. With replacement means you are replacing the item back to the container before you draw it, right? Every item is replaced back, and it's a simple random sample. So now I'll discuss other sampling technique also. So generally we take a random sample out of the population. Random sample means every member of the population has the same chance of being selected into the sample. Now there are two things. Let's say your population is of 5 lakh people, and you take a sample of 500. So 500 sample of 500 will be known to you, x1, x2, x500. So you can compute their mean. You add 500 observation, divide by 500, you will get what is called sample mean, which is denoted by S square. Similarly, you can get the variance of the sample observations. Variance of the sample observation is S square. S square you can compute, that is called sample variance. And sample proportion. Sample proportion means in the 500 observation, how many, let's say, males are there, how many females are there. You can count in 500 easily, right? So that is called small p. Now, these are the values which you can compute, because sample observations are available to you. So these are the value which you can be computed. You can compute sample mean, you can compute sample variance, you can compute sample proportion denoted by small p, right? And whatever you compute, and if your values are concerned with the sample, then it is called a statistics. For example, x bar is a statistics because it is concerned with the sample. S square is a statistic. It is concerned with the sample. Small p, it is concerned with the sample. So it is a statistic. But there is a population also. So if your values are concerned with the sample, then they are known as statistics. If your values are concerned with the population, for example, population mean. Now there are standard notations for you need to understand all these notations in statistics. Population mean is denoted by mu. This is the symbol we use for mean. Population variance is denoted by sigma square, standard symbol. Population proportion, that means how many males, how many females could be there in the population, is denoted by capital P. Sample proportion is small p, population proportion is capital P, right? Now, if your population of 5 lakh people, it's very difficult to compute all the parameters of the population. That's why we use a sample out of the population. So if your values are concerned with the population, they are known as parameters. And if your values are concerned with the sample, then it is called a statistic, right? Now, these are unknown. these are unknown because population parameters are not known to you. Population mean, population variance, population proportion, they are not known to you. They are not known to you. All right. So now what is the meaning? That means if you are using an appropriate sample size and you have used the appropriate sampling technique, then what you will expect? You will expect that this sample mean will give you an estimate of the population mean. That means X bar will give you estimate of this mean. Similarly, sample variance denoted by S Kr will give you an estimate of this population variance. And small p, which is sample proportion, will be an estimate of the population proportion. Hopefully you will agree with me. And we are referring back from the sample to the population. And this problem that you are able to estimate the parameters of the population based on the sample, and this defines your first word, that is called estimation. So estimation means how you can estimate the parameters of the population based on the sample. So this is the meaning of the first word, estimation. Hopefully it makes sense to you, right? Because population is difficult to study, but parameters can be estimated based on the sample. It is just like this. Whenever somebody is having a stomach infection or infection in some other part of the body, right? Your entire body is if your entire population. But whenever we give a sample, we give a sample of blood for testing. You cannot, some doctor cannot take your entire blood of the body and then test it. He will always take a sample out of the entire blood. But this sample is representing the entire blood of the body, right? So that is what do you mean by this sample? This is what do you mean by this population, right? Okay. So hopefully the first word is clear. Now question is, whatever the estimates you have obtained by using different sampling techniques, X bar, S square, P. Now, next question is whether they are good estimates or they are bad estimates, right? Whether they are good estimates or they are bad estimates. Now, what is the meaning of this? That means I need to test it. So before testing, we need to frame hypothesis. That's why we need to test hypothesis. So we need to frame hypothesis. So I will discuss about the hypothesis. Before that, let me tell you a little bit about sampling technique, how to take out a random sample from the population. Right. I think I missed that slide. Anyhow, okay. So these are the learning objectives here. The learning objectives are to understand the role of significance test, to distinguish between null and alternative hypothesis, to interpret p-value, type 1 and type 2 errors. All these things we need to understand. What is the meaning of p-value? What is the meaning of type 1 and type 2 errors? Then level of significance and the role of significance test. These are going to be the learning objectives. So I was discussing about the sampling techniques. So basically, there are some techniques which are meant for homogeneous population. For example, simple random sampling is applicable whenever population is more or less homogeneous in nature. For example, if I am teaching a class of 50 students and all of them, they are from the same background, then this group can be considered as a homogeneous population. I can use simple random sampling with or without replacement. But sometimes the population may not be homogeneous. It is going to be heterogeneous. And if there is a heterogeneous population, we generally apply the technique which is called stratified sampling. What is a stratified sampling? We divide the entire population into different stratas. Stratas are nothing but subsets of the population, with the assumption that within a particular strata, the population will be homogeneous. And if there is a variability will be between the stratas. Variability will be between the stratas, right? So then we take out the random sample from each and every strata, and so that it should represent the entire population. It should represent the entire population. So this type of technique is called stratified sampling. Then there are other sampling techniques like cluster sampling. Then there is a quota sampling. Then there is purposive sampling, right? Then probability proportional to size samplings. I mean, all the sampling techniques, they are helpful in different situations, how to take out a sample out of the population. Okay, with this background, So let's look into how to frame null and alternative hypotheses and all this. The first thing is, what do you mean by hypothesis? Now, some people say that there is a negative hypothesis, there is a positive hypothesis. I have also seen in some of the substandard books. Let me tell you, there is no concept of negative and positive hypothesis in statistics. Hypothesis, basically, if you look at the definition of hypothesis, this is the definition: a tentative statement regarding the population, not regarding the sample. A tentative statement regarding the population relating to a certain phenomena. Relating to a certain phenomena means relating to height, relating to weight, relating to BMI, etc., in which the researcher is interested, in which you are interested, right? Let's say my interest is to see whether this population has a mean IQ of 100. So I'm interested in IQ. That is a phenomena, right? And we want to verify on the basis of the sample. So let me just read the definition again. A tentative statement regarding the population relating to a certain phenomena, like mean of the population I want to test. Let's say somebody give me this task, that can I say that the mean IQ of this population is equal to 100? So if you go back to your population parameters, mean is denoted by mu. So I'll frame the hypothesis H0, null hypothesis, that mu is equal to 100, right? So this is the definition of the hypothesis. Now there are two types of hypothesis. One is called the null hypothesis, another is called the alternative hypothesis, and both of them are important to frame. So what is basically hypothesis? If you can specify your objectives of the study, if you can write down the objectives of your study into one or two sentences, basically they form your hypothesis, right? So what are the null and alternative hypotheses? Let me go through the next slide with the help of examples. Let's say somebody is interested in testing that the mean IQ of this population is equal to 100. Now, so whatever the claim the person is having, we always put it under H0, and the symbol for H0 is this one, right? So because we are referring to mean and the parameter in mean is mu, so I want to test mu is equal to mu naught, where mu naught is given to be 100. That mu naught is that value which is specified. So it is asking whether mu is equal to 100 or not, right? So whatever we want to test, we always put under H0 with equal to sign. With equal to sign, that mu is equal to 100. The mean IQ of the population is equal to 100, right? Okay. Now, next question is how to frame alternative hypothesis. Now, we are framing the null hypothesis. Alternative hypothesis is denoted by H1 or HA. H1 because we are writing 0 for null, so we generally write H1 for alternative. Or this you can say H0 and alternative write HA. It is up to you whether you want to write down HA or H1, doesn't matter, everybody understands. Now, if you are writing mu is equal to 100, that the mean IQ of a population is equal to 100, this is your claim. You want to test it. Now, alternative is it may not be equal to 100. It may be different from 100, right? So, alternative I'll frame that mu is not equal to 100. Now, if I'm writing not equal to 100, then it could be less than 100, it could be more than 100, because I'm just putting not equal to 100. It could be less, it could be more. That's why if there is not equal to sign in your alternative, then this type of alternative is called two-sided alternative. Let me just repeat, this type of alternative is called two-sided alternative. Why two-sided? Because it could be less or it could be more. So that's why it is called two-sided alternative. Now, sometimes you are 100% sure that this is a very good population, the students are very good. I am sure their IQ level will be more than 100. I am 100% sure. So if you are 100% sure, not 99%, if you are 100% sure, then we use one-sided test, that mu will be greater than 100, that your mean will be greater than 100. And sometimes you are also having that I am sure these are very dull students, they don't know much. So I'm sure that their mean IQ will be less than 100. If you're 100% sure, then this inequality will change and alternative will be written as mu less than 100. Right? Now, mu less than 100 is also one-sided, because less than or greater than means on the right hand side, less than means on the left hand side. So to distinguish between greater and less, we always write one-sided right tail. Right tail means it is greater than or on the right hand side, and one-sided left tail means it is on the left hand side. So one-sided left tail alternative, one-sided left tail right alternative, and one-sided left tail alternative. Okay, now this is two-sided alternative. Now question is, because in the population generally what will happen, we are not sure. We are not sure. So most of the time, 80 to 90% of the cases, we always take two-sided alternative. One-sided alternative is to be taken only when you are 100% sure about something. Then and only then. Let me give you an example of 100% sure. Let's say there are some patients, doctor has examined them and note down their blood pressure. And there are 20 patients who are suffering from low BP level. Their BP level is low blood pressure. Then doctor knows that there are standard medicines available in the market. People are using for the last 30, 40 years, very well-known medicines. So he gives these medicines to these 20 patients and asks them that you consume these medicines for 2 months and then report to me again. Then after 2 months, what the doctors will expect, because these are very well tested medicines, and so doctor will expect that after 2 months their low BP level should come back to normal level, right? So there the doctor is 100% sure, because they are very well tested medicines, right? There the doctor is 100% sure. So if you are 100% sure, then and only then we use one-sided. But if you are not sure what will happen in the population, then we use two-sided. Hopefully, how to frame null hypothesis, how to frame alternative hypothesis, some idea is clear to you. Now, it is not necessary that you always test mean. Sometimes we need to test variance also. So you can, let's say somebody has a claim that, can I say that variance of this population is equal to 5? Then the symbol for variance is sigma square. So my hypothesis will change. I will write down H naught, that sigma square equal to 5. And sometimes you are testing two equality of two means. For example, let's say there is a government school, there is a convent school. Now somebody is claiming that, can I say that the performance of both the schools, government and convent, is the same, or there is a difference? So what you will do, you want to test, let's say mean parameter of the population for a convent is mu1, for the government is mu2. So I'll frame the hypothesis. If there is no difference, so I'll write down that mu1 is equal to mu2. That means performance of both the schools is same, and alternative that they are not same, right? So this is how we need to frame null and alternative hypothesis. Okay, with this background, there are two important types of errors which we have in statistics. Look at the green line. No study is perfect. There are always chances of errors. So there are manufacturing defects always in any manufacturing unit, whether it is an industry or whatever, right? Now you know what is H naught, you know what is alternative now. So here I have written H naught is true, here I have written H naught is false, here is a decision reject H naught, here is a decision accept H naught, right? So your decision is reject H naught when H naught is true. What does this mean? H naught is true means something is of good quality, but it has been rejected. Something is of good quality, H naught is true. Something is of good quality, but it has been rejected. That means it is an error. It was a good quality, but it has been rejected. It is an error. And this type of error in statistics is called type 1 error. And this error is a very serious error. It happens in selection procedures. Let's say there is a very, very good candidate, right? And the committee also feels that this candidate is really good. But the second candidate is having pull or push, some political pressure, or maybe something else. And rather than selecting the first one, they select the second one. So H naught was true, but it has been rejected. Then university or the college has to suffer for how many years? They have to suffer for 30, 35 years. Deadwood planted for 35 years. And there are samples in each and every university. you know. So serious error has been committed right in the beginning of the appointment. And this type of error is called type 1 error, right? So type 1 error is reject H naught when H naught is true. In economics, this type 1 error is generally called producer's risk. Why? Because producer is producing good items, but it has been rejected, so it's producer's risk. So type 1 error in economics is generally called producer's risk. Now look at the type 2 error. Type 2 error is accept H naught when H naught is false. Something is of bad quality and you are accepting that. Let's say I want to buy apples and there are bulk of apples and I can see from their face that they are not of good quality. But the owner of the apple says, sir, you have to buy only half a kg or 1 kg. You just pick and choose. I just apply pick and choose technique, bring 1 kg and consume them. And because it was not a good lot, so I got food poisoning. My family also got food poisoning. And then somebody was admitted in the hospital, 10,000 rupees were spent. Whose loss is this? It's my loss because I accepted a bad lot. So that is called type 2 error. Accept H naught when H naught is false. Something is of bad quality, you are accepting that. So that is called type 2 error. And it's again a very, very serious error. And economics people, they call it consumer's risk because we have to consume it. So it's called consumer's risk. So remember, type 1 error is producer's risk, type 2 error is consumer's risk. And for any system to be better and better, we want these errors to be very, very small. You cannot expect everything to be 100% correct. So we want this system to be, with these errors to be very, very small. Now, what should have been the correct decision? Correct decision is accept H naught when H naught is true. Something is of good quality and you have also accepted that. So that's the correct decision. And here also you can look for reject H naught when H naught is false. Something is of bad quality. You also rejected. That's the correct decision. So these diagonals are errors and off diagonals are correct decision. Right? I'm just making you aware of that these technical things are very, very important to understand so that you can proceed with the testing part later on. Okay, these are few other examples of type 1 and type 2 errors. This is type 1 error, this is type 2 error. From the medical point of view, from the code point of view, I'll give you a few examples. Let's say, what do you mean by type 1 error? Type 1 error in medical field is also called a false positive. A false positive. What do you mean by this? The person doesn't have the disease, but the test says they do have. Now, right in the beginning when COVID-19 in 2020, there was no testing procedure and testing procedure were very weak, right? And let's say person doesn't have a disease, but test says that they have a disease. Then what will happen to the patient? What will happen to the person? He will be put into the hospital with other patients, right? And he was not having any symptoms or something, but he will develop it then because they are COVID-19 patients. That is called false positive. The person doesn't have the disease, but the test says they do have. This is type 1 error. What is type 2 error? Type 2 error is called false negative. A person has a disease. He was having COVID-19, but test does not pick it up. Test says, no, he doesn't have. He come back home. There are 5 members in the family. All of them will be infected. That's a wrong thing, right? That's called false negative. That's called false negative. So these are, again, very, very serious errors, right? Look at the court examples. Convicting an innocent person. Person doesn't have done any crime, but he has been convicted, right, by the court. So wrong decision. Look at not type 2 error, not convicting the guilty. The person has done a crime, but the judge has let him go. He was a criminal and he may kill a lot of other people. So very serious error, right? Not convicting the guilty is type 2 error, is again a very, very serious error. So these are the two types of errors we have to minimize as far as statistical decisions are concerned. Okay. Then we come across level of significance, and that is generally called alpha. Alpha means level of significance. Alpha is nothing but probability of type 1 error. probability of type 1 error, you know type 1 error, we want this probability to be as small as possible, as small as possible. For example, why it is called level? Level means you cannot go beyond this level. That's why it is called a level. Let me tell you the exact meaning of, because in many of the research paper it is written, we take alpha is equal to 0.05, we take alpha is equal to 0.01. Why? Why not alpha is equal to 0.23? Why not 0.30? Right? Why only 0.05 or 0.01? The reason is simple. Let's say if there are 100 oranges in the basket, and somebody bring me this basket, and he asking me that these are very good, you can buy it. I just by going through the inspection, I can see that they are of good quality. But let's say if 1 or 2 are of bad in between, doesn't matter for me. I will buy that lot, because you cannot expect everything to be 100. But there must be some limit. And the maximum allowable error in statistics is 5%. That means, let's say out of the 100, 40 are of bad quality. So I will accept that lot, or I will reject that. I will simply reject that lot. So that's why there must be some limit. So if 3, 4, up to 5 maximum are of bad quality, maximum up to 5 are of bad quality, I will accept the lot. But beyond that, I need to reject that lot. And that is called your alpha. That you cannot go beyond this level. And level of significance has to be fixed well in advance before conducting the experiment, depending upon the sensitivity of your experiment, right? So that is, alpha is nothing but probability of type 1 error. And then that's why we take this as, the smaller it is, better it is. We take alpha 0.05, 0.02 or 0.01. That is the reason. The smaller, the better. Okay. Then there is type 2 error. Probability of type 2 error is basically called beta. Probability of type 2 error is called beta. Now, beta as such is not important. The important part is 1 minus beta. And 1 minus beta is called the power of the test. And power of the test is directly related to your sample size and your sampling techniques. Let's say I have not taken the appropriate sample size, my sampling technique was not good, and I have performed a t-test or f-test and send it to some journal, and they ask me that what was the power of your t-test. Then when I computed the power, which is 1 minus beta, I came to know that the power was only 40%. That's why you are having objections. So minimum power required for any test is about 80%. You require 80% power, right? And it is directly related to your sample size, directly related to your sampling technique. That's why we look at the power. Then there is concept of p-value, and I will discuss this p-value in my next slide. Now alpha is fixed in advance. P-value will be given by the software. I will tell you how you will. Every time in SPSS, wherever it is written significance level, so that means it is a p-value. So only thing is which you need to check is, if you have framed the null and alternative hypothesis, then you have the alpha fixed like 0.05 or 0.01. P-value will be given by the software after applying the test statistics, and you reject your null hypothesis. Let me just repeat. You reject your null hypothesis if your p-value is less than alpha. If p-value is less than alpha, you reject your H0. Alternative will be accepted automatically, right? So for the time being, you just remember that p-value, if it is very, very small, less than alpha, we reject the null hypothesis. But if it is more than alpha, then you do not reject the H0. Then alternative will be rejected. You have to accept H0, basically, right? Okay, so this is the concept of p-value. Hopefully, some of you know normal distribution. So this is the diagram of the normal distribution. This is a normal curve, right? Now, let's say I want to test two-sided alternative, and I fix my alpha to be 0.05. Now, two-sided alternative means H0 mu is equal to mu naught, and alternative mu not equal to mu naught. When I say mu not equal to mu naught, then it is two-sided, because mu could be less than mu naught or mu could be greater than mu naught. And my error which I am fixing is 5%, let's say. Then I don't know whether it will be on the left hand side or it will be on the right hand side. So I equally divide this 5%. Equally divide this 5% means 2.5%. 5 by 2 is 2.5%. And this green color area, which I'm leaving, which is shaded as green, is basically 2.5 on the left hand side and 2.5% on the right hand side. And this region is basically called, because it is error, this is called rejection region. So this is your rejection region, right? This is your rejection region. And this white area is basically your acceptance region. Now, if some of you may be aware of the standard normal distribution, then it is a two-way table. If you know the probability, you can compute point, and if you know the point, you can compute probability, right? For example, what is the probability of this green area, which is a rejection region? 2.5%. 2.5% means 0.025. 2.5% divide by 100, you will get 0.025, right? So no, I know the probability. If you know the probability of this from the standard normal, you can compute this point, and it will come out to be 1.96. It will come out to be 1.96. So I have computed on the positive side. There is no need to compute on the negative side because normal distribution is symmetrical. So if this is 1.96, this will obviously be minus 1.96. So we call this as Z alpha by 2, and we call this as minus Z alpha by 2. So one thing is clear, you compute the value of the test statistics. If it is greater than 1.96 or it is less than minus 1.96, then it will go into the rejection region. You will reject your hypothesis. But suppose your computed value is coming out to be 1.25. It is 1.25. So 1.25 obviously will lie somewhere here in the white region. Somewhere in the white region, right? And you cannot reject your hypothesis. It will be accepted. Now, what is p-value then? Area outside this line or area outside the computed value. So if your computed value is exactly 1.96, then outside this area is p-value. So outside this area is 0.025, outside this area is 0.025. So it is 0.025 plus 0.025. That is equal to 0.05. If your exact computed value is exact computed value is 1.96. Okay. But suppose your computed value is 1.25. See what is written at the top. P-value is nothing but area outside the computed value. So let's say 1.25 is somewhere here. So if you drop a line here, and the rest of the area outside will increase, that means green region will increase. Green region will increase and it will be more than 0.05. And once it becomes more than 0.05, it will go into the white region. That is your acceptance region. You cannot reject your H0 because you are falling into the acceptance region. Similarly, let's say your computed value is coming out to be 2.73. Now 2.73 will come somewhere here because it is 1.96, then will come to then 2.5, 2.7, and minus 2 point will be this. Then green area will become very less because a p-value is outside. So your p-value will become very less. And if your p-value become less, obviously it is definitely going into rejection region. So you will reject your hypothesis. It will be less than 0.05 straight away. So that's why in most of the softwares, you don't require any statistical tables. Alpha is fixed, p-value will be given. You just need to reject H0 if p is less than alpha. Once p is less than alpha, it is going into the green region. You are going to reject it. But if it's more than 0.05, it will go to the white region. So there is inverse relationship between p-value and computed value. If your computed value will be higher, p-value will be small. And if your computed value will be small, p-value will be higher. Right? As simple as that. So that is the relationship or the idea about the p-value. So smaller the p-value, greater chances of rejecting the null hypothesis. Higher the p-value, greater chances of accepting the null hypothesis. Please note down these things, right? Okay. Now, if you have any question up to this, please, before I move on to parametric test, if you have any question up to this, type 1, type 2 error, critical region, and p-value, hypothesis framing, If you have any question, you can ask me. Yes, please. Is there any question up to this? Yes, please. Any question up to this?
No, sir.
Is it clear now? Everything is clear? I mean, you can spend 2-3 minutes. We have time. If you want to ask any question up to this, you can ask me. Or should I move on? Yes, please. Tanushri madam, Mansi, anybody? If you have question, Manas Pal, if you have any question, you can ask me. Otherwise, I'll move on.
No, sir, no question.
Okay. All right. So I think the type 1, type 2 errors, null hypothesis, alternative hypothesis, parameter statistic, right? And
Hello, sir.
yes, please.
सर
Yeah.
पॉपुलेशन सर पॉपुलेशन मीन एंड सैंपल मीन इसमें जो कॉन्सेप्ट आपने बताया था और एक बार प्लीज रिपीट कर दीजिए.
Yeah. Population mean means the value which is associated with the population, and population is difficult to study. So population mean is denoted by mu, and it is a parameter because it is the value which is concerned with the population. I cannot study the population, so I'll take a sample. Let's say sample of 200 people, sample of 50 people, or sample of 100 people. Then if I'm having, let's say, height of 100 people or weight of 100 people, I can easily compute their mean. That is x bar, right? So x bar is a statistic, which is your sample mean. You can compute out of the sample observation, but population mean you cannot compute. Mu you cannot compute. So our testing procedure is about mean mu, population mean mu. So that is the difference between population mean and the sample mean, right? Is it clear? Yes, please.
Yes, sir.
Yeah. Anybody else? Anybody else? Okay. So let me move on to now the parametric test. And why they are known as parametric test? Because in parametric test, there are certain assumptions. And if those assumptions are satisfied by your data, then they are known as parametric test. For example, observation must be independent. Observation must come from normal distribution. Now, this is the major assumption. That's why I put this into blue line. Observation must come from normal distribution. Now, how to check whether your data is coming from a normal or not? Just wait. I will tell you the methods. There is histogram, there is a box plot, there is a quantile plot. Then there are two exact methods like Kolmogorov-Smirnov test. Then exact method like Spirovilk test. We will discuss all this. So whether your data is coming from a normal distribution or not. Then the third is the hypothesis must involve population parameter. What are the population parameters? Mu, sigma square, capital P. So your hypothesis, null hypothesis must involve all these parameters like mu is equal to mu naught, or sigma square equal to something, or mu1 is equal to mu2, or sigma 1 square equal to sigma 2 square, and so on. So if your data is coming from a normal distribution, your hypothesis has a population parameter, your observations are independent, then and only then we can apply parametric test. So let's go to the parametric test. Rest of the things are not important. Now, how to check the normality of the data? How to check the normality of the data? There are three graphical procedures. And one of the graphical procedure is called histogram. Everybody knows histogram. So if you draw the histogram of your data, and it is almost symmetrical. Last time we discussed about skewness and kurtosis, if you remember, that your shape of the histogram is almost symmetrical. That means if you drop a line from the center, area on the left and right, they are same, then you can say that your data is approximately normal. Like height data, weight data, BMI, all these are considered to be approximately normal in anthropometric parameters. Then another is box and whisker plot. Box and whisker plot is another important plot. Today we will draw it and tell you how to interpret the results. And there will be median line. If median is right there in the center of the box, then your data is normally distributed. But if it is below or above, then your data may not be normally distributed. And the third type of plot is called quantile plot, which I'll discuss today, that how to check the normality of the data. Then there are two exact procedures also. They are known as non-parametric test. One of them is called KS test. KS test is generally called Kolmogorov-Smirnov test. With the help of this, I can also check the normality of the data. Another is Spirovilk test. But let me tell you, graphical procedures are better than these exact procedures. Graphical procedures are better. We use the exact procedures only when you are somewhere you are in a fix. Should I accept? Should I take this as normal or not to take this as normal? In that situation, sometimes we apply these tests. Okay, here is a situation. For example, look at the shape of this histogram. Now, this is the highest bar. Let's say I drop a line. This is the normal curve. This is the normal curve, right? So if your data would have been normal, all these bars, they should have been within this curve. Are they? No. There are some bars which are outside. So immediately you will say that this data is not following a normal distribution. The data hasn't come from the normal distribution. Another way to look at, you drop a line from here. How many bars on the left hand side? From the highest bar, you drop a line. There are 3 bars on the left hand side, but how many bars on the right hand side? 8 or 9. So it is not symmetrical. It is not symmetrical means the data is not coming from a normal distribution. Look at this one. Now, if you drop a line from here, the number of bars on the left and number of bars on the right, they are approximately same. Approximately same. So if they are approximately same, you can consider this data to be approximately normal. Not exact, but approximately normal. And for such type of data, you can apply parametric test. But here you cannot apply. This is how we draw the box plot. Last time, if you remember, I discussed about the quartiles. Quartiles divide the data into 4 equal parts, right? For example, median divides the data into 2 equal parts. Median divides the data into 2 equal parts. Once you arrange the data in order, look at the middlemost value, that will give you median. That means half of the observations are below this and half of this above this. Same way quartiles. So this is called the first quartile. This is called the third quartile. How to compute these quartiles? Suppose I take a very simple example. You can compute it immediately. Suppose there are 100 observations, right? You arrange the 100 observations in increasing order from the lowest to the highest. From the lowest to the highest, right? Then first quartile means 1/4 of the data. So 100 divided by 4 will be 25th. So 25th value, whatever is, after arranging the data in order, 25th value will be your Q1. And what will be Q3? 75th value. How to get 75? 3 into 100 divided by 4. And I mean 3 into n divided by 4. You will get 75, right? So then you draw a box between Q1 and Q3. This is the shape of the box. And this is called median. If median would have been right there in the center, that means area of the upper box would have been same as the area of the lower box, then you will say that data is coming from a normal distribution. Data is coming from a normal distribution. But here you can see the lower area is less, upper area is more. So obviously data is not coming from a normal distribution. This is the picture from the histogram of the same data. This is the picture of the box plot from the same data. Same data, it's age data, all the values between 18 to 63. I mean, range of the age data was 18 to 63. This was the interpretation using box plot. This was the interpretation using histogram. And both of them, they say the same thing, that data is not normally distributed. And same is here, that is called quantile plot. What is a quantile plot basically? Let me tell you what do you mean by quantile. Suppose I am having 30 observations. You arrange the observations in order, 1 to 30. Then obviously your first observation will form 1/30th part of the data. Hopefully you will agree with me. Second will 1/30th part of the data means just 1/30th part. And second observation will form 2 by 30th part of the data. Third will form 3 by 30th part of the data. These are known as quantiles. So these are the quantiles which are of your data. These all dotted line, dotted circles. They are the quantiles of your line, quantiles of your data. And then there is a standard normal quantile. If your data would have been normal, your points must be along a straight line. But here you can see there are deviations here, there are deviations here. So again, the same thing, same inference, that the data is not normally distributed. If all the points they would have been on the line, then data is normally distributed. It's the same data, age data. You can draw histogram, you can draw box plot, you can draw quantile plot, same information from all the three graphs. So this is how to check the normality of the data. Now, moving on to parametric test, there are two types of parametric test. One is for large samples. Whenever your sample size is more than 30 is considered to be a large sample. And another are for small samples. Small samples, whenever your sample size is less than 30, like 15 observation, 8 observation, 9 observation, 20 observation, right? So if your sample size is very large, generally we use Z test or Z statistics. But when your sample size is small, we use T test. Now today, it has been mentioned that I have to cover the T test only, because T test is used for small samples. And the advantage of T test is when your sample size becomes large, then basically your T test approaches to Z test. So whether you apply Z test or you apply T test for large samples, you will get the same result about testing of hypothesis. So if it is you are likely to get the same results for large samples, that means T test can be used for small samples and T test can also be used for large samples, right? So in most of the softwares, particularly in SPSS, there is no Z test then, because if sample size is small, you use T test. If it becomes large, again use T test, because it's approximately equal to Z test. So that's why in many of the softwares, only T test is given, not Z test. Now where to use T test? Because this is one of the problems which we need to solve today. It can be used for testing of the single population mean, like mu is equal to mu naught. It can be used for testing of the two population means, like H naught mu1 is equal to mu2, convent school, government school. Or it can also be used for testing of the paired data. Paired data means sometimes we have pairing of the data. Let's say before giving the treatment, as I mentioned, suppose 20 patients, they are suffering from low blood pressure. How the doctor will come to know? He has noted down the blood pressure of these 20 patients without giving any treatment. So 1 to write up to 20, X1, X2 up to X20. Now give them the medicine for 2 months. It's the same set of patients. They are not independent. And you call them after 2 months. So and again note down their blood pressure. Let's call this as Y. So Y1, Y2, Y20. X1, X2, X20 were the previous values before giving the treatment. Y1, Y2, Y20 after giving the treatment. So if your medicine is effective, that's why it is called pair. Pair means before and after, X1, Y1 first pair, X2, Y2 second pair, just like left and right shoe. So data is present in pairs. That's why we call pair t-test. And in pair t-test, our aim is to test. Suppose there is, I subtract the two, yi minus xi, and all the differences are 0. If all the differences are 0, do you think the medicine is effective? No, it was the same blood pressure, and after giving the medicine, you are getting the same thing. So the differences are 0. So medicine is not effective at all. So to check the effectiveness of the medicine, we look at the paired data, and t-test is also used for checking the correlation coefficient. Then f-test is used for to test the equality of variance. H naught sigma square equal to sigma 1 square equal to sigma 2 square, right? Then there is one-way ANOVA, two-way ANOVA. All this will be discussed. So let's take a practical example of one sample t-test, independent t-test, pair t-test. So all these examples. Now, first is, can we say that the mean weight of a certain population is different from 60? You are observing some population and you are guessing that mean weight of this population is likely to be 60. So this is your claim, you want to test it. Mean, parameter of the population in mean is H naught. H naught means your parameter is mu. So you frame your hypothesis H naught that mu is equal to 60. Alternative, it is not equal to 60 because I don't know what will happen in the population. So there is only one value, only one parameter, that is called weight. Phenomena is weight. So that's why this is called one sample t-test, because your interest is in testing about weight only. Your interest is testing about weight only, whether weight is equal to 60 or it is different from 60. One sample t-test. Then does the mean weight in two regions differ significantly? Now it comes to two sample problem, because there are two regions now, just like government school and convent school. Or if it is relating to weight, let's say somebody is interested in testing whether the mean weight of people from West Bengal or people from Northwest region, whether their mean weights are similar or there is a difference. So if their mean weights are similar, what I'll expect H naught, that mu1 is equal to mu2. That means there is hardly any difference between the mean weights of Northeast and West Bengal. They may be different. So this is called independent t-test. Why it is called independent t-test or two sample t-test? Because West Bengal is one population, Northeast is another population, just like government school, just like convent school. So you are dealing with two parameters here. So this is called two sample t-test or independent t-test, or sometimes name is also given student t-test. Now, as I mentioned, that in case of the pair t-test, you have X observation before giving the treatment, Y observation after giving the medicine. You find out these differences, and if the mean of the differences, which is denoted by mu d, if mu d is equal to 0, that means all the differences are 0, then obviously the medicine is not effective. Alternative, it is not equal to 0. So this is a problem of testing pair t-test. So hopefully one sample t-test, where to apply, two sample t-test or independent t-test, where to apply, or the pair t-test. So I'll give you a practical demonstration now, where to apply these tests. So this is the formula for computing one sample t-test. Let's say I want to test H naught, mu is equal to mu naught. Or let me take this hypothesis that mu is equal to 60. So your mu naught is 60, right? So this is the t-test I have to use. So what is this t-test? It is nothing but if there are, let's say I take a sample of 100 people. So based on 100 people, I'll compute the sample mean, that is X bar. I'll compute the sample variance by using this formula. And then apply t-test. X bar minus mu naught under root of Sx square divided by N. Right? And we say that this is having t distribution with n minus 1 degrees of freedom. Why n minus 1 degrees of freedom? Because degrees of freedom are nothing but basically how you divide your S square. You are dividing by 1 over n minus 1. So this is counted as a degree of freedom. Another way of expressing the degree of freedom is through the definition. So maybe you can write down the definition for degrees of freedom. Degrees of freedom are nothing but the number of independent observations which form FORM, which form the statistic, minus the number of restrictions. Let me just repeat. Number of independent observations which form the statistic minus the number of restrictions. Minus the number of restrictions. So here there is, how many observations are involved in X bar? N number of observations. But what is the restriction? Restriction is that we are subtracting X bar, mean from each and every observation. So that's why your degrees of freedom will be n minus 1. N is the number of observations. Because of this restriction, it is n minus 1. So that is the reason. So this is having t-test. So from the sample observation, you will compute S square. From the sample observation, you will compute x bar. Under h naught, mu is equal to mu naught is given to you. N is the sample observation. Everything is known. So you can compute the value of t. And once you compute the value of t, SPSS will give you p value. Right? And once you get the p value, then you have to take a decision. Alpha is fixed, say 5%. You just need to check whether your p value is less than alpha, then reject h naught. More than alpha, you accept h naught. As simple as that. So let me give you now demonstration, because we will have to complete t-test one by one. Okay. All right. So let me take up this example. And I already have some kind of data. Okay. Just a minute. The file will open in SPSS. It will take about 30-40 seconds. Now it's coming up. All right. So BMI is called body mass index. Hopefully the screen is visible. Yes, please. Anybody?
Yes, sir.
Okay. Now experiment is like this. Please try to understand the experiment for one sample t-test, and then you will be through. There was some population, I mean people, some researcher like you was observing the people in that area, and after 2-3 years he realized that weight of the people is increasing. Then idea struck to his mind, why not to check their BMI levels? Why not to check their BMI levels? BMI means stands for body mass index, right? Now how this body mass index is computed? You look at the weight of the person in kg, kilogram, and then height in meter. Height in meter. So if you have this weight and height, and then you can compute BMI. So what is the formula for computing BMI? BMI is nothing but, yes please.
Weight divided by height in meters cube.
Yeah. So BMI we compute. I think in the first exercise which I have given you, it was there. So BMI is nothing but weight in kg divided by height in meter square. Square is only in the denominator. Height. For example, if somebody is having, let's say, weight 60 kg and height is 1.57 meter. So its BMI you can compute. BMI will be 60 divided by 1.5 square, 1.57 square. So you will get BMI. So he has computed the BMI levels, and these are their BMI levels. First person has BMI 23, 25, 37, 39, and so on. Right? So he has taken a few sample of our people and computed their BMI. Now what is the problem? He wants to check whether this population has a normal tendency of BMI levels, or people are moving towards obesity, or people are moving toward overweight problem, right? Or they are having any underweight problem. So roughly you can note down, please, if you are having a copy, pen or pencil, that if your BMI level is less than 20, although cutoff is 18.5, let's take roughly, if your BMI level is less than 20, the person is considered to be underweight. But if person's BMI is between 20 to 25, the person is a normal person, right? Normal person. And if the BMI level is between 25 to 30, then person is considered to be overweight. Person is overweight problem. And if it is more than 30, BMI is more than 30, then the person is moving towards obesity, right? For example, look at fourth number person. BMI is 37. So this person is moving towards obesity. Next one is also moving towards obesity. And this one person, which is 21, is almost normal. But whenever we talk in the statistics terms, we have to look in totality. What is the overall performance of this population towards obesity, towards normality, or what? right? Okay. So what is our hypothesis here? First of all, we want to check whether this population has a normal BMI level or not. Normal BMI level or not. So normal level is between 20 to 24. Normal BMI level is between 20 to 25, sorry, 20 to 25. So I can take any value for testing, 23, 24. So you can write down mean BMI level we need to check H naught. Your H naught will be mu is equal to, let's say 24. I want to check mu is equal to 24 and alternative H1 that mu is not equal to 24. So let me just repeat null hypothesis. Mu is equal to 24. Why 24? Because it lies between 22 and 25. I want to check. Suppose I accept the hypothesis. If you accept the hypothesis, that means people are normal. There is no hue and cry. People are absolutely normal people, right? Okay. But if I reject this hypothesis, then obviously you have to see whether there is an underweight problem or overweight or obesity problem. I will answer this question and it is given by t-test. So hopefully you have written the null hypothesis. Mu is equal to 24, alternative mu not equal to 24. All right. So for this, we will apply t-test. So go to analysis, go to compare means, and in compare means, this is called one sample t-test because we have only one sample BMI. So it says, what is your test variable? Your test variable is BMI. So you shift this to this side. Then it is asking test value. Test value is that value which you have put under H naught. That's why under H naught there is always equal to sign. So your H naught is mu is equal to 24. So I'll put the 24 value here. That is what I want to check. Right? And in options, it will give you some kind of confidence intervals, nothing. That's all. So this is one sample t-test. So what? So press OK and you are getting the result. So here is the result in front of you. There are 25 observations. This is mean of the 25. This is standard deviation of 25. Right? Standard deviation means it has computed this. Let me tell you what it has computed. This is your X bar. This is your mu naught. And what is standard error of mean? Standard error of mean is nothing but standard deviation divided by under root of n. 7.003 divided by 5. Under root of n, under root of 25 will be 5. So if you have 7.003 divided by 5, you will get 1.401. Right? And if you see our slide, your X bar is 31 point something, your mu naught is 24, and the denominator is standard error. Your denominator part, whatever is there in the under root, that is your standard error. So I can substitute all the values and you will get the t value. And corresponding to this t value, there will be p value. So this is, if you substitute all the values, how to substitute? 31.04 minus 24 divided by 1.401, you will get answer as 5.025. So software has given you answer 5.025. And how many observations were there? 25. So degrees of freedom will be one less. So it will be 24. And this is your p value. So this is your p value. Wherever in SPSS it is written significance, that means it is a p value. So if you double click, you can write this as p value. You can write this as p value. P value. Of course, there is no need to write. This is just I'm telling you that wherever in SPSS it is written significance, that means it is a p value. And smaller the p value, greater is the evidence against null hypothesis. But remember, p value is never 0. P value is never 0, and your p value is showing that this is 0. Actually, it is not 0. I can prove it. If you double click here, right, and then right click and go to the cell properties, and in cell properties you go to format value, go to numbers and increase the decimals. Let's say I make this 13 decimal and press OK. Then you can see the exact p value. Actually, this is the p value. P value is never 0, right? So, but what we were getting 0.000. If somewhere you are getting 0.000, then you must put this P value as 0.0001. Why 1? Because there will be some decimals which we truncate at 1. So we write 0.0001, right? So 0.001 is less than 0.05. Your alpha is 0.05. So what you will say? We will reject the hypothesis or we will accept the hypothesis. Our hypothesis is mu is equal to 24. Alternative mu not equal to 24. Your P value is coming out to be less than alpha. So will you reject or will you accept? Yes, please.
Reject.
Yeah, who says reject? Yeah, you are
Reject.
absolutely right. We will reject the hypothesis. Reject the hypothesis means that the claim which you are making that this people are having normal BMI level is rejected. Is rejected because they are not having normal BMI levels now. The question is whether they are having overweight, underweight, or obesity problem. Look at the mean. What is the mean BMI now here? Can you tell me what is the mean BMI level here?
31. So it is obesity.
31. And 31 is beyond 30. 31 is beyond 30. That means people are moving towards obesity. So entire crux of the doing this exercise is that people are moving towards obesity, and what you were looking at that the people are moving towards obesity was the correct one. In fact, you have tested the normal BMI levels. So you have to go to the people, you have to ask them that please don't eat pizza, burger, noodles. Your weight is increasing. You are facing obesity problem. You must keep track of your health. So all these things you can give some kind of advice. So this is called one sample t-test. Yes, please. Is it clear? One sample t-test is clear?
Yes, sir.
Yes, sir.
Okay, very good. So let's move on to two sample t-test now. And just going back to the presentation, what is a two sample t-test? This is actually the two sample t-test. This is called independent t-test, or sometimes we call the student t-test, or sometimes called two sample t-test. So there will be two samples, one from convent school, another from government school, something like that, right? Or one from West Bengal population, another from Northeast population. So let's say it is a very simple experiment. There are two types of groups of people. One group of people, they like very much the pizza diet, and another group of people, they like, people like us, they like normal diet, dal, chawal, roti, right? So we want to compare the differences. Let's do one exercise that both these groups, one group is given pizza, breakfast, lunch, dinner, all the 3 times pizza, and the another group is given the normal diet, right? And they have been given for 1 month, and after 1 month we want to check their weight gains, whether those people who are consuming pizza, they are having the more weight than the previous one, or those who are having the normal diet, they are having more or less. So to compare the differences in two groups. So to compare the differences in two groups, we use two sample t-test, right? So at the end of the month, we measure the weight gain of each participant. So weight gain of the pizza diet people, weight gain of the normal diet people, we are writing this as mu1 and mu2. And we are testing mean weight gain mu1, mean weight gain mu2. So if there is no difference between pizza diet and normal diet, hypothesis will be mu1 is equal to mu2. Alternative, because I don't have any idea in the population what will happen, mu1 is not equal to mu2. So one group is on pizza diet, another group is on normal diet. So two independent groups. So that's why it is called independent t-test. So for independent t-test, this is the formula which we use. We take out a sample of groups which have consumed pizza diet. Let's say n1 number of people, those who have consumed pizza diet. So they will be having n1 minus 1 degree of freedom. And those who have consumed normal diet, n2 number of people. So degree of freedom will be n2 minus 1. But it is two independent samples. So total degree of freedom will be n1 minus 1 plus n2 minus 1. So this will give you n1 plus n2 minus 2. And then I am looking at the mean weight gain. So mean weight gain for those who have pizza diet is x1 bar. Mean weight gain those who have normal diet is x2 bar. And then I can also compute their standard deviations or variance s1 square and s2 square from both the samples. And then I compute this what is called pooled variance, which is the formula given. You will not have to go through the formula. So that is s square. So once s square is known, I compute this statistics. X1 bar is known to me, weight gain of the pizza diet people, mean weight gain. X2 bar is known to me, S square is known to me, N1, N2, everything is known. So I will get a T value and P value, right? And with this much of degrees of freedom. Now, I'm having two different populations. Here is very, very important point. Please try to understand. One is put on pizza diet. Another is put on normal diet. Now, first of all, these two are independent populations. Before applying t-test, the software just check whether these two populations, because we are testing about mean, mu1 is equal to mu2. But there is another parameter which is variance, and I am silent about variance. Let's say variance, those who have consumed pizza diet is sigma 1 square. Those who have consumed normal is sigma 2 square. Now in the population, because it is just based on the sample, in the population parameters for variance is sigma 1 square for pizza, sigma 2 square for normal. So first of all, it will check whether their variances are equal or not. So another hypothesis will be tested that will test sigma 1 equal to sigma 2 square. Sigma 1 equal to sigma 2 square. And that test is basically called F test. Whenever we are testing the equality of variances, here we are testing equality of means, mu1 is equal to mu2. But suppose I want to test sigma 1 square equal to sigma 2 square, equality of variances, then it is tested with the help of F test, right? So now this is one of the formula I have written. This formula is applicable only when sigma 1 square equal to sigma 2 square. So first of all, sigma 1 square equal to sigma 2 square will be tested with the help of F test, right? If they are equal, then this T value will be computed. But if they are not equal, that sigma 1 square is not equal to sigma 2 square, then another T value will be computed. And the formula is very complicated. I have not written here. And degrees of freedom will come out in points in that case. So there will be two T values. Whenever we apply independent test, there will be first T value, there will be second T value. So when to choose first one, when to choose second one, if your variances hypotheses are equal, that means F value, there will be F value will be given to you and its P value will be given. If that P value is non-significant, use the first T value. But suppose F P value is coming out to be significant, then use the second T value, right? So that's why we apply F test first and then check the means. So hopefully the independent T test is clear to you. Let me go through the demonstration part. I'm just closing this file and open some another file. Okay. T test. This is T test. Just wait, file is opening up. Okay. Now experiment, please try to understand the experiment. And once the T test will be completed, I'll give you a break. And then we will move on to chi-square test and F test. I'm just doing it right now. And then discriminant analysis in the later part. Okay. So here is experiment is like this. Please try to understand the experiment just like we understood the BMI experiment. There was an industrialist and he want to hire people for his industry. And there were two types of people. One group of people, those who have done post-graduation, and the other type of group that was there which have done only graduation. Right? Now, it is a semi-skilled type of work. People from graduate, people from postgraduate, both of them, they can do the job. But one idea struck to his mind, that why not to check their BMI levels? Sorry, not BMI, sorry, IQ levels. So why not to check their IQ levels? Let's say if I prove that IQ levels of PG group and undergraduation group, they are same, then obviously the industrialist will hire people from undergraduate. Why? Because less educated people, he will pay less salary. If he hire people from post-graduation, he has to pay more salary. So to save his salary, he is just trying this experiment. Whether the mean IQ levels of both the groups are same, that is his claim. And if they are same, obviously he will hire people from the undergraduates. But if there is a difference, then he has to be careful whether PG group is better or UG group is better. Hopefully you are able to understand the crux of the experiment. Is that clear what I'm trying to say? Yes, please.
Yes, sir.
Yes, sir.
Okay. So this is how you have the feed the data. What I did actually, noted down the IQ levels of the PG group, and then PG group is having how many people? It is having about 27 people, and in front of that I have written 111. Then later on I have given the label. You know how to assign the label, that one is PG group, and then below that, once the one PG is over, then two start with UG group. So 96, these are IQ levels. So in the first column you have IQ levels, and in the second column you have group, and two types of group, either PG or UG. Right? This is how you have to feed the data for two independent t-test. Okay. Now, what is our hypothesis? Please write down H0. Mu1 is equal to mu2. Alternative, mu1 not equal to mu2. Mu1 not equal to mu2. So this is what we want to test. Right? Okay. Mu1 is equal to mu2 stands for that the IQ levels of PG and UG group, they are same. And if you accept the hypothesis, obviously he will save the money because he will hire people from the UG group. But this hypothesis is rejected, when it will be rejected? If the p value will be less than 0.05. So let's test his claim. Analysis, compare means, independent t-test. Test variable is your IQ. Grouping variable is your this group variable. Now it says define groups. Define group means define your levels of groups, PG and UG. This is what we mean by this. So that is what we have written 1, group 2 is 2. But suppose there would have been metric students also. But t-test will at a time compare two. Let's say I want to compare undergraduate and metric. Post-graduation, not post-graduation. Then they are given group code as 2 and 3. Then I'll write 2 here if I want to compare and 3 here. So that's why you have to specify which group you want to compare. Continue. And then you go to options. In options, you will not have to do anything. So that's all. So that statistics will be computed, but you will get 2 t values. Why 2 t values? Because first of all, it will test whether sigma 1 square equal to sigma 2 square or not. Whether the variances of PG and UG group, they are same or not, by using F test. That is called Leven's F statistics. So that will be computed. I'll show you. Press OK. Experiment has been done. Shift it to this side so that you can see a clear picture. So there are 27 people in PG group, 61 in UG. These are their mean IQ levels. along with standard deviation, standard error of mean, right? And here, these are the two t-values. This is the first t-value. This is the second t-value. Which one to choose? We need to, because first of all, it is testing variances. Variances are tested by using f-test. So f-test is, your H0 is sigma 1 square equal to sigma 2 square. And if you apply that test, this is the p-value. Now, is this p-value is greater than 0.05 or less than 0.05? Yes, please.
Greater than.
Greater than. So you are testing the hypothesis sigma 1 square equal to sigma 2 square. So the hypothesis will be accepted or rejected? Hello?
Rejected.
Rejected? Anybody else? Because p-value, once p-value become more than 0.05, you cannot reject your hypothesis. P-value
Yes,
to be rejected.
sorry.
P-value to be rejected only when. Yes, please.
Yes, sigma 1 square is equal to sigma 2 square accepted.
Yeah. So here your answer is because our H0 was sigma 1 square equal to sigma 2 square, that hypothesis will be accepted. That hypothesis will be accepted. If the hypothesis is accepted, I will look at the first t-value. But suppose this would have been rejected. Suppose this would have been 0.017. Then it would have been less than 0.05. So rather than looking at the first value, in that case, I must look at the second t-value. Right? This is the t-value you have to look for. And why the degree? But now I will see only the first t-value. Why degrees of freedom are 86? Because n1 minus 1. n1 is your 27. 27 minus 1, 26. n2 minus 1. 60 minus 1, 60. So 60 plus 26, 86 degrees of freedom. That's why. Now here the degrees of freedom can come in points. But I have to see the first t-value. There are two t-values. So hopefully you understand where to use f-test. F-test is used for testing the equality of variances. If both of them are equal, take the first t-value. But if they are unequal, take the second t-value and its p-value. But fortunately, both the p-values are same. Doesn't matter. So now this, actually this is the test statistics we want. So this p-value is less than 0.05 or more than? Yes, please, anyone. Is this less than 0.05 or more than?
Less than.
Less than. So our hypothesis was H0 that mu1 is equal to mu2. So will this hypothesis be accepted or rejected?
The alternate hypothesis will be accepted.
Yeah.
This hypothesis will be rejected.
Yeah, hypothesis, null hypothesis will be rejected.
Null hypothesis will be rejected.
That means his claim was that IQ levels of PG and UG group, they are same. That has been rejected. That has been rejected. So that means he was thinking that I will hire people from UG group. No, he has to hire people from which group? Now, which group is better? You go through their mean. You see mean of PG group is 95, mean of UG group is 79. So which is having better IQ? PG or UG?
PG.
PG. So he will have to hire people only from PG group. This experiment he was doing just to save his money. So that his claim was not true and he has to hire people only from PG group. That was this entire exercise, comparing the two independent groups. Is that okay? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, okay. Now the last t-test and then we can take a break and then come back. Last t-test is called paired t-test. Before and after situation. Before giving the treatment, after giving the treatment. And you can apply it anywhere, not only in medical field, you can apply it anywhere. For example, okay, let me just go through the data of paired t-test. Just wait for a moment. The file is opening up. Okay. Now, this is before giving the treatment observations. This is after giving the treatment. So it's the same group of patients. They are not independent. One is before giving the medicine, after giving the same thing you can apply on you also. Let's say right in the beginning, if Daya Shankarji have given you some performa and it is relating to some correlation, regression, then skewness, kurtosis, mean, median, mod, t-test, null hypothesis, and some questions are there. Now, please mute yourself. Please mute yourself. Yeah, thank you. Yeah, okay. Now, if right in the beginning, before giving the training, Daya Shankarji has given you that whatever you know, just test your knowledge. So you have fill up that performer. Now, after 10 days, he hand over the same performer to you. Now you again fill it up. So this is before getting the training scores. This is after getting the training scores. Which one will be better, after or before? Yes, please.
After.
After will be only when you have learned something. But suppose before and after all the differences are zero. If all the differences are zero, do you think the training is effective? Yes or no? Suppose all the differences are zero. Then the training is not effective at all, right? So it can be applied in various situations. And that's why this is called paired t-test. Persons are same, while in case of independent t-test, persons were different. One group was PG group, another was UG group. Here the same persons evaluated at two different time points. Before and after. So what is your hypothesis? So it will be, hypothesis will be like this for paired t-test. This will be the hypothesis which we will test, that mu of D is equal to 0. That means population mean difference is equal to 0. And if you accept H0, that means the medicine or the training is not effective at all, because all the differences in totality are 0. But if you reject this hypothesis, then obviously medicine is effective. How to apply this test statistics? You find out all the differences, yi minus xi. You will get d1, d2, d3 right up to dn. And based on all the differences, you compute the mean of the differences, you compute the standard deviation of the differences, and then compute this t. So this is mean of the differences, standard deviation of the differences divided by under root of n. Now it's just one sample. One sample means once you compute the differences, it is just one sample, and degree of freedom will be n minus 1. So this statistics will be computed. That will test this hypothesis. So let's apply this to our data and check the result. Go to analysis. Go to again compare means. Go to independent t-test. Independent t-test. And in independent t-test, sorry, not independent t-test. We have to go to paired t-test. Sorry. Yeah, paired t-test. This is paired t-test. Paired t-test before, after. It is not necessary. You can put it any order. You can put after, first, before, later. Doesn't matter. P-value will not change. P-value will be same. And here, nothing to be done. That's it. So you will get t-value and p-value. So this is what you are getting the result. Okay. So these are their before means, this is after means, and before and after mean is this. This is your D bar. And the denominator, which was under root of this is 2.4008. That is denominator. So D bar is minus 6.55. Divide by this, your T value will be this, minus 2.729. There are 20 pairs, so degree of freedom will be 1 less, 19. And this is your P value. So P value is less than 0.05 or more than 0.05. Yes, please. Yes, please. Less than 0.05 or more than 0.05.
Less than 0.05.
Less than 0.05. So if it is less than 0.05, that means hypothesis is rejected or accepted.
Accepted. Oh, rejected. Rejected.
हाँ, अभी भी कंफ्यूजन. रिजेक्टेड. आप सब लोग एक काम करिए, एक बड़ा सा पेपर लीजिए और बड़ा बड़ा लिखिए उस पे बड़ा बड़ा लिखिए रिजेक्ट H0 इफ P इज लेस देन अल्फा. उस पे बड़ा बड़ा लिखो रिजेक्ट H0 if P is less than alpha. Otherwise accept H0. I mean if P is greater than alpha. और ये कागज का बड़ा पेपर लिख के और जो अपन आपके घर में फैन है ना जहां पे आप सोते हैं उसके ऊपर चिपका दीजिए, ताकि जब भी आपको कंफ्यूजन हो तो कम से कम फैन से भी नजर आए कि रिजेक्ट H0 when P is less than alpha, राइट? सो ये आपके माइंड में बिठा लीजिए एक बार, इसको कहीं पे चिपका दीजिए कि P वैल्यू विल बी लेस, T वैल्यू विल बी हायर, और if T वैल्यू विल बी हायर, P वैल्यू विल बी स्मॉल. सो इसमें T जो आ रहा है 2.7 आ रहा है, हायर वैल्यू है, P वैल्यू विल बिकम स्मॉल. सो reject H0 when P is less than 0.05. Okay, so you were rejecting the hypothesis. If you are rejecting the hypothesis, what was the hypothesis? Mu D is equal to 0. That has been rejected. That all the differences are not 0. That means yes, the medicine is effective. Yes or no?
Yes, sir.
Yes.
So that is the conclusion. So that is the conclusion which we have drawn, that the medicine is effective. So this
Sir.
completes your detail. Yes, please.
सर एक बार फिर से ये कंफ्यूजन बहुत इसमें रिजेक्टेड और एक्सेप्टेड में, प्लीज सर आप एक बार
Okay. इसको ध्यान में रख लीजिए. ये लाइन याद रख लीजिए, इसको बड़ा बड़ा लिख लीजिए. रिजेक्ट द नल हाइपोथेसिस इफ P वैल्यू, यहां पे लेस करिए, इक्वल टू भी करने की जरूरत नहीं है. P वैल्यू इज लेस देन अल्फा. अल्फा इज फिक्स्ड इन एडवांस. देखिए आपको नल हाइपोथेसिस एक्सेप्ट करना है, रिजेक्ट करना है. इट इज ओनली नल हाइपोथेसिस. वंस यू रिजेक्ट द नल हाइपोथेसिस, अल्टरनेटिव विल ऑटोमेटिकली बी एक्सेप्टेड. And once you accept the null hypothesis, alternative will always be rejected. So acceptance or rejection is only for the null hypothesis. Rejection or acceptance is only for the null hypothesis. So if you remember this line कि P वैल्यू जितनी छोटी होगी, अगर वो 0.05 से कम हो गई तो समझ लीजिए कि रिजेक्शन हो गई. क्यों रिजेक्शन? क्योंकि आपका ग्रीन रीजन में चला गया वैल्यू, और ग्रीन रीजन इज नथिंग P वैल्यू, एरिया आउटसाइड द कंप्यूटेड वैल्यू. तो अगर आउटसाइड द कंप्यूटेड वैल्यू 2 पॉइंट समथिंग यहां पे होगा, दैट्स वाई वो T की वैल्यू जो 2 पॉइंट दिखा रहा है ना, 2 पॉइंट समथिंग, वो ग्रीन रीजन में चला गया, दैट मीन रिजेक्शन रीजन में गया. अगर ये 1.96 आपकी आके अगर T वैल्यू आती 1.37 तो ये डेफिनेटली एक्सेप्टेंस रीजन में जाता, क्योंकि 1.37 पे यहां पे आप लाइन लगाते, -1.37 पे यहां पे लाइन लगाते, और आपका ग्रीन एरिया बढ़ जाता, तो P वैल्यू बड़ी हो जाती, और P वैल्यू जब बड़ी हो जाती तो आप उसको रिजेक्ट नहीं कर सकते. सो रिजेक्ट H0 व्हेन P इज लेस देन अल्फा. यस प्लीज, इज दिस क्लियर?
यस सर.
Yeah. So there should not be any confusion. So this completes your T test. Now just after the break we'll come back and we will do F test हो गया आपका, T test हो गया, सारा आपका type 1, type 2 error, level of significance, critical region, P value, थोड़ा सा sampling भी हो गया, null hypothesis, alternative, everything I have done. Now after the break we will go for chi-square test, and chi-square test will take maybe around half an hour, and in the last hour we will do about discriminant analysis, and by 7 hopefully you will be free. Yeah, any question?